Hi, this is an example of how to find a Laplace transform with a delayed forcing function. So a student has asked me about this question, and I'm going to do it in gory detail, and I'm going to do it via two methods. So imagine we have this function here. I'm going to call it f of t. This is question number 12 from section 6.3. So the function is a delayed forcing function. It's a t minus 3 multiplied by the unit step function at time 2 minus t minus 2 multiplied by the unit step function at t equals 3. The first thing we're going to do is draw a picture of what this looks like, what the function looks like. Okay, so when the function is before time 2, it's at 0 because neither of these unit step functions have kicked in. So just to remind ourselves, let us just draw a quick graph of u2 of t. u2 of t looks like this. There's u2 of t. That is u2 of t. And then similarly, u3 of t looks like this. There is u3 of t. Okay, so we're multiplying t minus 3 times u2 of t, and then we're multiplying negative of all t minus 2 times u3 of t. So up until time t equals 2, nothing happens. So now we're going to just draw a graph of f of t. So here's what I'm thinking, sort of in terms of maybe thinking of it in cases. F of t is going to be 0 when t is less than 2. And then when t is between 2 and 3, so now I'm thinking between 2 and 3, what's going to happen? Well, the second part hasn't kicked in, so it's going to look like this, t minus 3. And then after time 3, t greater than or equal to 3, what is it going to look like? Well, there's still going to be the t minus 3 part will still be there, and then we will have also the new part, t minus 2. So that I can simplify that, in fact. So I would represent that function there for the time when the function is greater than or equal to 3. I would represent this here as, well, t minus t, then I got minus 3 plus 2, so this would simply be minus 1. So let me just rewrite it in the cases. F of t looks like this, 0 until time 2, and then it looks like t minus 3 between time 2 and time 3, and then it looks like minus 1 when t is greater than or equal to 3. So I could draw a picture of that. That looks like this. Nothing's happening until time 2, and then here at time 2 the function is t minus 3, so that'll be, this number right here will be negative 1 when t is 2. 2 minus 3 is negative 1, and then at time 3, that's going to be here, that's going to go up like that, and then what will happen is when it's bigger than 3, it's simply going to be here like this at minus 1. So that is a graph of f of t. Okay, so you want to be able to go from the case statement version of the function to the version of the function using the unit step function. You need to be able to go back and forth, and then you should also be able to draw the function. Okay, then now we're gonna find the Laplace transform of this function using two different methods. So method one is going to be using the Laplace transform table, and method 2 is going to be doing it from the definition of the Laplace transform. So let us take a look here at method number 1 using the table of known Laplace transforms. Okay, that's going to be our first idea of what to do. Let's just rewrite the function so that we have it in front of us. And the function is this thing here, f of t equals t minus 3 u2 of t minus t minus 2 times u3 of t. Okay, then let me just go to the table and get the relevant Laplace transforms from the table. So that would be the Laplace transform of t. I can see I'm going to need to use that. That is 1 over s squared. Then I'm going to be having these delayed functions. So I'm looking at the table and seeing, oh, what does that look like? So there's two more relevant pieces of information I'm taking from the table. That is the Laplace transform of the, whoops, let me get rid of that if I can. Shoot, bonk the keyboard. The Laplace transform of the Laplace, I'm going to just, let me get rid of that. Sorry about that. I bonked the keyboard. Let me, I have to lasso this or something to get rid of it. Okay, it's not working. All right. Let me just, let's just scrunch that out and keep going. So, okay, so the Laplace transform of, where was I? Here, UC of t from the table. That is going to be e to the minus CS over s. And then also from the table, the Laplace transform of UC of t multiplied by f of t minus c. That is e to the minus cs times the Laplace transform of f of t. Okay, that's the three relevant facts I'm going to use from the table. Okay, so now let's take a look at how to manage this one here. I think I understand possibly why this question has been asked, and it's a good question. First, we're going to look here, and we see that this value of c is here, and that value of c is also there. And then when we look here, we say, uh-oh, it's not lined up the same way, right? There I've got a 3, and there I've got a 2, and on this one I've got a 2, and then this one I've got a 3. So how do I handle that? I'm going to write it out so that that problem goes away. And this is how I'm going to do that. I'm not going to be able to change what's on the unit step functions, that 2 there and the 3 there. That's not going to be possible to change. But what I can do is write this function here and this function here slightly differently. Let me show you how to do that. That will then look like this. F of t equals 2. And I will going to write t minus 3 like this, t minus 2, thinking of that sort of as one piece, and then minus 1, because that is still t minus 3. And then I've got u2 of t, and then I'm going to write this one in this manner, t minus 3, thinking of that as one piece, and then I'm going to have plus 1 times u3 of t. Okay, why did I choose that? I chose that because here now I have the situation where I have t minus c and c. And here I have t minus c and c. In this case, the c is 3. And in this case over here, the c is 2. So that aligns with what I can read from the table. That is the reason for doing that. And then I'm going to distribute the unit step functions. That will look like this. F of t equals t minus 2 times u2 of t minus u2 of t. And then on the next one, I'll have minus t minus 3 u3 of t minus u3 of t. Okay, and now things are looking really, I think, good. I think the bulk of the problem is now solved, because I can use this fact right here, this one right here, alongside with this fact here, or the Laplace transform of t, and I can simply now write out the answer. So I'm going to go ahead and do that. I'm going to write here f of s, the Laplace transform of f of t is, and then looking at this one here, that is going to be the delayed version of t by 2. So that's going to e to the minus 2s, and then the Laplace transform of t, which is s squared, 1 over s squared. And then I have here the Laplace transform of u2 of t, and then that is simply directly from the table, minus e to the minus 2s divided by s, and then I do exactly the same thing for this pair right here. So I'll have here minus e to the minus 3s over s squared minus e to the minus 3s over s. And I'm done. So now I have the Laplace transform of the for the delayed forcing function using the table. So that was method one from the using this information in the table. Okay, now I'm going to just, before I go to method two, which I'm going to do directly from the definition of the Laplace transform, I'm going to take a look at this function, which I've drawn here, f of t, and I'm just going to write it in this manner here, f of t. I mean, this is indeed what it looks like. It is 0. It is 0. We had this up above, but just so I can see it on my screen here. Well, actually, you know what? Because I'm going to go do the next, I'm going to do it down here. I'm going to rewrite it again. So that is the answer right here. That's the answer via method one using the table. Now we're going to move to method two using the definition of the Laplace transform. Method two, definition of Laplace transform. You're going to see in this case, this is more time consuming. But on the other hand, if you don't see how to manipulate the functions, like as I did in the previous thing, you can always fall back on using the definition of the Laplace transform, so long as your integration skills hold up to it, because sometimes those integrals can be a little bit difficult to do. So let us do that right now, and so we'll just rewrite the function that we're taking, the Laplace transform, right here. So, and we're going to write it in the case method representation. So that's going to be 0 when t is less than 2. It's going to be t minus 3, and that's when t is greater than or equal to 2 and less than 3, and it's going to be minus 1 when t is greater than or equal to 3. Same function, but we've put it into the case statements. Okay, so then I'm going to do the Laplace transform of f of t is going to be the integral from 0 to infinity of e to the minus st f of t dt. And now that I've got the function in a bunch of cases above, I can simply set up the integral in piecewise. And so what I'm seeing is the function is 0 until 2, so there's nothing to integrate. And then between 2 and 3, my function looks like this, t minus 3 e to the minus st dt. And from 3 to infinity, my integral, my function is just simply minus 1. There. Okay, so now actually the problem of finding this Laplace transform has turned into a integration problem. So I think in some sense, from our perspective, the problem is solved. You know how to integrate, and then if you don't make any mistakes in the integration, then you will find that that you get exactly the same answer that we just got from using the table. I will go through and do this in detail should you care to follow through on that. So what does this look like then? I'm going to separate the integrals a little bit. F of s will be this. I will have the integral from 2 to 3 of t e to the minus st dt minus 3 times the integral from 2 to 3 of e to the minus st dt plus the integral from, oh no, I'm going to get the minus sign on the outside there, minus the integral from 3 to infinity e to the minus st dt. Okay, there we are there. Okay, this first one, I'm going to the first of these three integrals, I'll just maybe make a different color so you can see what I'm doing. I'm going to first evaluate the first of the three integrals. I'll do that by integration by parts. Let me do that separately, and then I can combine it back with the other two. So now I'm going to first take a look at the integral from 2 to 3 of t e to the minus st dt, and I'm going to do it by parts. And I'm going to have u is equal to t, du is equal to dt, and dv is equal to e to the minus st dt, and v is equal to minus e to the minus st over s. Okay, so setting up for by parts, and then the integral will be equal to let's see, uv, that's going to be minus 3 e to the minus 3s over s. Nope, let's try that again, sorry. That is going to be minus t e to the minus st over s. That is u times v evaluated at 2 and 3, and minus the integral of v du. V is negative, and v du is going to then be e to the minus st over s dt. Okay, and then I can keep going. I put those, I evaluate this at those two numbers. That I get this here, minus 3 e to the minus 3s over s plus 2 e to the minus 2s over s minus, and then I do that next integration, which is going to be e to the minus st over s squared, evaluated at 2 and at 3. I keep going. I get minus 3 e to the minus 3s over s plus 2 e to the minus 2s over s minus e to the minus 3s over s squared plus e to the minus 2s over s squared. Okay, so that is this integral here, the integral from 2 to 3 of t e to the minus st dt. There it is. Okay, now I want to go back, having done that first integral, I want to go back and do the other two integrals and combine all of the terms. So I'm now back here looking at f of s, which is that first integral that I just figured out. That is, let me just write it. I'll write it again. Minus 3 e to the minus 3s over s minus, plus, momentary pause here while I make sure I don't make a mistake, plus 2 e to the minus 2s over s minus e to the minus 3s over s squared plus e to the minus 2s over s squared. Minus 3. Okay, then I have minus 3 times the integral from 2 to 3 of e to the minus st dt minus the integral from 3 to infinity of e to the minus st dt. Those are straightforward integrals. This one here just being the exponential function over s, and then this one, let's make sure I don't, 3 to infinity, 2 to infinity. Let me see, I've got this one also being the exponential function over s. Same. Okay, so let me just write those out so we can see what's happening here. I'm going to be down here, I'm going to have this here. I'm just, there's a little bit of rearranging of terms possibly. Let me just get them here. Minus 3. What happened here? I've got a plus. Sorry, I don't want to lose a minus sign here. I've got a minus 3. Oh yes, so it's going to turn to a plus 3. Okay, fine. So I'm here minus 3 e to the minus 3s over s plus 2 e to the minus 2s over s minus e to the minus 3s over s squared plus e to the minus 2s over s squared. And then here I'm going to have plus 3 e to the minus st over s evaluated at 2 and 3. That's that second integral. And here I'm going to have plus e to the minus st evaluated over s evaluated at 3 and infinity. Okay, at as t goes to infinity, that is going to, e to the minus st is going to go to 0. S is greater than 0. That leaves me a whole bunch of terms that I can combine and evaluate. So now I just expand this and I expand this. I combine any like terms and do any cancellation that I can see, and this comes out to be e to the minus 2s over s squared minus e to the minus 3s over s squared minus e to the minus 2s over s minus e to the minus 3s over s. Same answer, of course. A little bit more time consuming and possibly a little bit more error prone doing it from the definition of the Laplace transform, but of course you can do that. Yep, so there it is. Two methods to do that with the delayed forcing function. Thank you very much, and I'll be posting another little bit of a review lecture coming early next week.